We come to our next speaker. The talk is about disentangling perceptual and analytical processes in solving Euclidean and non-metric travel salesman problem. And it's given by Arman Baradaran.
Yeah, thank you so much for that introduction. So, hello everyone. Today I want to talk to you about traveling salesperson problems, or TSPs for short. So you should prepare yourself to see some more dots. But chances are that, if you know what TSPs are already, that you probably haven't seen mentions of them in a while. So I'm really very pleased to be sharing this work with you, and thank you for sticking around until this Tuesday, the last day of VSS. So if you haven't seen TSPs before, if you just need a refresher, TSPs are combinatorial optimization problems where the goal is to travel through a set of cities and return to the starting city, and making sure that you're visiting every city in between. For example, I'm showing you 6 cities here, and I would wager that most, if not everyone in this room, if you're starting at the top left, would produce this kind of tour through this 6-city problem. Now, the reason that TSPs are interesting in cognitive science is that there's n-1 factorial possible tours, and this, with small increases to the number of cities in the TSP problem, the problem really quickly becomes computationally intractable to solve. You have for 6 cities, you have 60 possible tours. For 16 cities, the number of tours quickly explodes to the number of neurons in the human brain. 21 cities, it's the number of seconds since the Big Bang. 60 cities, it becomes the estimated number of atoms in the universe. And most importantly, with 82 cities, it becomes the hypothesized number of positions in chess. So here's the thing. Even with 80-city TSPs, if you give it to a human to solve, they can quickly produce good solutions that are within 10 to 15% of the optimal. And thanks to multi-resolution pyramid models, which are directly inspired from the structure of human vision, we already kind of know why humans are good at TSP. In fact, there was plenty of work 20 to 30 years ago showing that these pyramid models, be they graph-based pyramids, like in our case for today, or image pyramids that are using wavelets and blurring and these such things, these can provide good human-like solutions to TSPs. And you can be sure that this work is not too recent because, as you can see, my advisor Zig was still at Purdue in 2006 when his lab brought TSP to VSS for the first time. But since then, despite some productive work in the 2000s, TSP was discussed at VSS only twice more. That's 16 years. How come there's been nothing else? Do we really know all there is to know about how humans solve TSPs? Spoiler alert, I don't think we do. And I would almost even go so far as to say that the field has been focused a lot on studying human behavior in TSPs through just a perceptual lens, for 30 years since the original paper from McGregor and Ormerod in 1996. Now, fair enough, I suppose, you can't blame vision scientists for being prone to tunnel vision, but before going into what we're thinking about the analytical side of matters, let me give you a tour, if you will, of how the pyramid model actually works. So the first step, So here's what we know so far, right? The first step is hierarchical clustering. There's 2 steps. The first one is hierarchical clustering, and I would say this is the most interesting one. Suppose I'm showing you, this TSP problem with 50 cities. Hierarchical clustering starts building the pyramid from the fine direction. So you're seeing all the cities, and your first step is to just make a set of clusters. And here I'm showing that set of clusters. We use the Boruvka algorithm. I'm showing you that set of clusters using Voronoi diagrams, right? So you're seeing there's a lot of polygons, and each of these polygons is holding a centroid that is being kept in that layer. And you start going into a coarser direction, in a coarser representation, as you go higher in the pyramid. So it becomes polygons starting to get merged until you're left with very few. And each of these polygons, you're holding kind of the centroid of these polygons. And you start building the tour at the coarsest region. So you go from a coarse to fine direction when you're building the tour. And this is easy, right? This is a 5-city, like on the coarsest section, this is a 5-city problem. the tour is really easy to build just using cheapest insertion. And you start going and building the subclusters of the tour on and on until you reach a fully built tour back at the finest side of the pyramid. So how are these tours actually produced, these subtours? Well, we're using the cheapest insertion heuristic. And this cheapest insertion heuristic is this second step of the pyramid model in which we're iteratively refining how the tour is being built. Right? So suppose we're zooming in on 3 cities, and I'm saying cities like this because these could be like centroids because it's in the higher layers, that must be visited in the middle of your tour, right? These 3 points. Now, for these 3 points, right, we're checking each permutation of these points to find the shortest one, or the cheapest one. So for example, let's say this is one possible permutation. This is another permutation. This is yet another permutation, right? And because you know the entrance and exit, kind of, in a sense, of how you're entering the points, there's less permutations that you have to check. So that's one way the heuristic works. So you reject these 2. Even visually, you know that this third one is the cheapest one, and this is the one that we keep. And this goes on and on for each subcluster within each layer that I showed you in the previous slide, right? Now, the pyramid model with these 2 steps of hierarchical clustering and iterative refinement, it matches human performance in more than one way. In 2006, Pislow and colleagues showed that tours produced by this pyramid model tend to have a similar error from optimal to human tours, and that their computational complexity is often linear or near linear, depending on the exact implementation of the model. And this kind of aligns with the timing and tendencies of human behavior in TSPs, as shown by Dry and colleagues in 2006. But in the real world, I would say it's pretty rare to be making decisions in spaces that are both metric and Euclidean. Usually, the distance between the points isn't the only thing you're considering as like a possible cost in the problem. So sometimes, there's obstacles in our path, and I'm, not just talking about life, I'm talking about TSP problems too. So Van Drunen and colleagues in 2022 kind of extended this classical TSP to include line segment obstacles that participants had to navigate around when they were producing their tours. So as it turns out, the pyramid model, with those very 2 same steps that I explained earlier, still matches human performance, which kind of suggests that these perceptual processes we're talking about are sufficient in handling spaces that are not Euclidean, but still metric. So to us, this begs the question, what about spaces that are non-metric too? So what we did is we added a new rule. We said each city is given one of 2 colors. Switching between cities that have different colors is incurring this penalized cost that is equal to double the Euclidean distance between the cities. Now keep in mind, we're saying this is non-metric because when you introduce this switching cost, you get a violation of the triangle inequality in about 40% of the possible triplets of cities. So, you know what? Here, try it out. What are the best tours in this example of a 6-city TSP? Right? If these were all the same color, you would immediately see a rectangle. You would draw the rectangle, and you're instantly done. But now that I've introduced this new rule to you, you probably have to spend a little time to grind those gears and think through the problem. And if you're paying attention to how the rule works, you might realize that doing a zigzag is the optimal tour to minimize the number of switches that you're doing. So what about this case, right? You're thinking again, you're kind of thinking about there's clusters, but it's a rectangular shape. Turns out still a zigzag is the best tour here. But what if I draw those lines even further apart, right? Do you still think a zigzag is the best tour there, doing that zigzag in the middle? Maybe not. And I'm going to show you the tour step by step because it gets a little harder to see, right? You switch here instead, and you move up to the city, switch, and you go back up, right? So choosing where to make color switches turns out to be pretty important in the non-metric TSP. And there's clearly something beyond how you're perceiving the colors and the problem, the points in the problem, right? So what we did is we gave 30 of these 50-city non-metric TSPs to 31 participants, and what we found is the following. Now, what I'm showing you here are not TSP problems, right? This is a scatter plot of results with the error from optimal on the x-axis and the number of color switches that the participants did on the y-axis. Right? So some subjects are performing pretty poorly, and some subjects are performing pretty well, almost as good as they would in the fully Euclidean case of the problem. Right? Some subjects are really minimizing the number of switches that they're willing to do, whereas others are kind of really more willing to actively engage with the thought process of thinking through where to make switches. That is not to say that by making more switches you can substantially improve your tours. You have to really try to optimize your switches because, as you can see, Concord, the star right there, Concord on average makes 10 switches. So how do you cluster in a non-metric space? How do we tell the pyramid model to do that clustering? Spoiler alert, we don't. We actually just convert to a metric space first. We use multidimensional scaling, right? Because multidimensional scaling can actually produce a Euclidean approximation from that non-metric input. But we have to ensure that this input isn't actually being misleading, right? Because the MDS is being given all of the pairwise distances in a problem. So here in this plot, I'm showing you that, in blue, you're seeing all the possible edges in a TSP tour. And in yellow, I'm showing you specifically the ones that are used in good tours, in the optimal tour in this case, right? So you can see that the edges, the long distance edges, are really never used in good tours. So what we did is we gave the MDS scale versions of each TSP to the pyramid model that I described before. And just as a note, we used the 3D approximations because they were better than the 2D ones, but going to higher dimensions did not improve the result. So how do we make sure that the MDS is not misleading? We use power weighting. We power weight the pairwise distances such that the longer distances are de-emphasized, right? So here I'm showing you when we do no weighting, this is what the MDS approximation looks like. You see two planes pretty far apart. As we introduce a little down weighting on those long distances, the planes start to get a little closer. And when we do even more of this kind of weighting, the two planes get even closer, right? And this is what the results are for each of these versions, right? So for the one where we do no weighting, the pyramid model results just always does two switches, and it does relatively poorly. And as you increase that weighting, it keeps doing more switches, and these switches turn out to be good switches because the error is also decreasing. Right? So the pyramid model with this weighted MDS front end is matching human performance. This is the same plot of human performance that I showed you before. And here I'm going to show you in quick steps what the pyramid model results look like. Right? So with no weighting, you have results on the bottom. And those four colors are just different depths for the cheapest insertion. The higher depth is always doing better than the lower depth. Right? And as you increase the weighting parameter, this keeps going kind of higher and improving, doing more color switches and improving the tour. And here in the kind of diamond shape, I'm showing you the case where we do the color switching cost inside of cheapest insertion without MDS. So you can see that they're using a lot of this, it's using a lot of color switches, and those color switches are not good. So that's why we knew that hierarchical clustering is the one that has to account for color switches. So I'm going to breeze through the implications of our results. There's two strategies, one that is a perceptual clustering and one that's an analytical pre-processing. There's individual differences that arise in how the problem is represented, and these are being represented through those analytical processes that I mentioned. And kind of participants are adopting qualitatively different strategies when solving these non-metric TSPs. And this kind of this flexibility, this human flexibility to balance the emphasis of local and global structures is what we think kind of might be indicative of somewhat of a core feature of cognition. And to investigate this, what we're doing is collecting more data on specifically chess players' performance on these non-metric TSPs. So that said, see you next year with those results. Feel free to get in touch with me if you have questions or via LinkedIn. Thanks so much.